Hello everyone, I am Provakar and the title of my project is Improving Security and Reliability for Replicated Data in Distributed Systems by Autonomous Trust Management. Nowadays, modern distributed systems actually replicate data to different geolocation area. So you may ask the reasons why replications is necessary because data is replicated to different locations so that first reasons I can say about low latency so that users can his data more quickly. For example, if this is the data source and this is the user, so then the users to get the data, here the data needs to cross this path. But if the data become available here, then the users can get it in a faster way. Another reason is high availability, so that data becomes highly able to the users. Another reason is scalability, so that more components can be easily added and maintained in the systems. And I think most important reason is fault tolerance. Like if, for example, one or more components are downs, so that the to make ensure that the whole system is not down, others component can work as backup for the down component. So these are the reasons for why modern distributed software applications replicate data to different locations. Okay. Now, data replication requires consistency so that read-write request to any replica will return the latest updated data. I mean, if a user asks to a replica, but the replica gives the user old data, then the motto of data replication is kind of violated because users always expect latest data. But this is a requirement. This is not the problem. Now I'll tell what the problem is. So there are several consistency protocol. On popular consistency protocol in replicated data systems is eventual consistency that makes sure that all the replica will be consistent eventually. And actually, majority of the uh, applications that use replicated data, they follow eventual consistency protocol. And but the problem is that this consistency protocol allow a replica to propagate its modification across the systems without being checked by others replica. So what can happen? Manipulated data that can be due of external attack or ill-conceived data that can happen by sensor malfunction will propagate across the system. Because, I mean, for example, there is a replica A, who has some wrong data. The reason can be manipulation or maybe sensor malfunction, whatever it is. But the thing is that replica A has wrong data. Now replica A propagates this data information to other replica. So if the others replica without any verification accept this request, then they all will start containing wrong data also. So eventually the whole system will start containing wrong data. So that's the problem. Uh, so in this project, I propose to use trust to determine if a synchronization request should be accepted from a replica or not. So the first portion shows the traditional approach in replicated data systems. So requester replica initiated a merge request and receiver replica without any verification accept the request. So that is the existing approach. Now in my project, I proposed here. So the requester replica will initiate a merge request, but here instead of accepting the request without any verification, receiver replica will check if the request is legitimate or not. If the request is legitimate, then the receiver replica will accept the request and update its local copy according to the requester replica. But if the request is not legitimate, then the requester replica, the requested replica will reject the request. So that's my proposal in this project. Uh, Here's the contributions in my project. So I have tried to integrate autonomous trust management to existing replicated data structures. This trust management will determine if a synchronization request should be honored or not. And then I have designed service level agreement SLA to define expected behaviors of a replica. So actually I have used SLA to design a set of rules that will determine uh, what kind of behaviors from a requested replica should be accepted, or what kind of behaviors will violate the rules, and in that case a request from a replica will not be accepted. And to secure communication between the replica, I have used asymmetric encryptions, and for every synchronization request, I have persisted the relevant information, so that I can build so that each replica can build up a behavioral history of others replicas. Okay, so this is my system design in this project. So this is the overall replica, and from the diagram we can see that it has four parts: TM, PRD, SLA, and TL, and there is a workflow. First, I will explain what these parts like TM, PRD, SLA, TL are. Then I will explain the workflow. So normally existing replicated data systems, replica, keep a local copy of data, which is called persistent replicated data, or PRD in short. So from this diagram, you see the PRD, persistent replicated data. Actually, this is common. I mean, existing replicated data system already contain this. And you may ask the questions, why persistence? Why it is called persistence? Because I mean, persistent data structure is a kind of data structure where users can access the previous versions but cannot modify it. So here is the same. If if a replica has some, if a replica's value is updated, then it is updated. Users can see what are the previous versions of that replica, but users cannot modify the previous versions, because what is done, it is done already. Like for example, there are several versions like version 1, version 2. So users can see what the value of a replica was, what the value was in version 2. Users can see it, but users cannot undo it, because based on version 2 already there are some others version have taken place, like version 3, 4, 5, etc. Okay, so this is why it is called persistent replicated data. I mean, users can access previous versions but cannot update it. Okay, so already existing CRDT replica contain this PRD. In this project, I propose to integrate three components with this replica. The first component is trust manager. Here, this one, the trust manager. It acts as a decision maker for all trust related issues. So actually, trust manager, I can say it the brain of a replica, because it decides if a synchronization request from others replica should be accepted or not. Then the another part is service level agreement. So this on service level agreement. So actually it is a set of rules. It describes uh, what should be the properties of data so that it can be accepted, and what should be the behavior of requester replica so that a synchronization request from the replica can be honored or not. And the third component is trust ledger. So it tracks the up-to-date trust value of others replicas. So now I will explain the workflow. So in this project, I propose to integrate three more components: trust manager, trust ledger, and service level agreement. And PRD, these components actually already existing replica contains that. Okay, so if a merge request come, so then trust manager will communicate with trust ledger to fetch what is the current trust value of the requester replica is. Okay, then trust manager will consult with service level agreement if the request has the attribute so that it can be accepted or not. I mean, if the request maintains the expected behaviors or not. So then service level agreement make the decision. So based on the decision, then trust manager decides whether to accept the data or not. So whatever happens, whether it is accepted or rejected, trust manager persists the relevant information to PRD and update the trust ledger accordingly. I mean, in this project, whatever happens, if a request is accepted, then trust manager upgraded the trust value of the requester replica so that for future request, the requester replica is considered more trustworthy. But if a replica makes Not legitimate request. In that case, trust manager downgrades the trust value of that requested replica so that for future request that particular replica is considered as less trustworthy. So this is the overall system design. Now I'll talk about implementation. So uh, as replicated data structure, I have used PN counter. So PN counter, this counters value can be both incremented and decremented. And to implement a distributed system with replicated data, I have used SymPy, which is a discrete event simulation framework provided by Python. And I have done a modifications of SymPy. Actually, in SymPy there are several processes, so I have done some modifications so that every process can be considered as a replica. And in SymPy replicas, I mean actually process, and I have modified the process so that the process can be considered as replica, and the replica communicate among themselves using a broadcast pipe. So this is the workflow using the modified SymPy. So message generator, actually message generator is done by the processor. So actually each replica generates a message, and here the message means synchronization request. So after making a synchronization request, the requested replica puts this message in the broadcast pipe. After that, the broadcast pipe broadcast the message, I mean the synchronization request. Then the message consumer, which is the requestee replica, so they receive the message from the broadcast pipe, and then they consult with the service level agreement. If the service level agreement said yes, then the requestee replica accept and persist the synchronization request. But if the service level agreement says no, then the requested replica rejects the request. So in SymPy, normally message generator, broadcast pipe, and message consumer, SymPy provides this, but I have done the modification so that actually message generator contains the synchronization request, and here I have done the modification so that the message consumer, I mean the requestee replica, consult with the service level agreement. So here is a simple screenshot of the service level agreement I have used in this project for PN counter. So I have defined the rules here. So this portion actually, uh, so I have tried to integrate trust for every replica. So actually every replica will have an extra attribute which is called trust. So actually every replica will have a trust value, and the trust value will be distributed. I mean, so actually, for example, replica A will maintain here. Actually, this is the task of the trust ledger here, the trust ledger. So, for example, replica A has its own trust ledger where it keeps tracks what is the trust value of others replica. Like for example, replica B, replica C, replica D, whatever. Similarly, replica B will contain its own trust ledger in which it will note down the trust value of others replica, for example replica A, C, and D, something like that. And this value actually distributed means based on the previous interaction, this value can be different. For example, for replica A, the trust value of replica C can be 90%, for example. But for replica B, the trust value of replica C can be 80%, because this can happen based on the previous interactions, based on the previous synchronization request history among these replicas. Okay, so now let me explain the specified rules. Here D means delta. So that here it means if the delta value of data is less than or equal 12 and the trust value of the replica is between 90 to 100, then the request will be accepted. So here, if the trust value decreases, then in that case, accepted delta range will also be decrease. Like here, if the replica has trust value between 65 to 89%, in that case, if the delta value of the synchronization request is less than or equal to 10, then in that case it will be accepted. Similar, the others will specify that if the trust value in between 50 to 64% range, then the accepted delta range is less than or equal to 8. So this is the rule actually I have used for this project. Okay. Now I'll talk about some encryptions. So to ensure secure communication between the replicas, I have used asymmetric encryption. And to implement the asymmetric encryption, I have used a Python open source package, PyCryptoDome. So this was the modified SymPy workflow in this project. Okay, now after integrating the asymmetric encryptions, some more things have been added here. So message generator, normally before message generator push direct message in broadcast pipe, but here first the message is encrypted using a public key, and after encryption that message is put back in the broadcast pipe. Broadcast pipe then as usual like before broadcast the message, and message consumer now gets the message from the pipe, but after getting the message, it decrypts the message using RSA private key. You can ask the question why asymmetric encryption? Because in asymmetric encryption, there exists two key. The requester replica use the public key, which is used to generate the private key by requester replica. So requester replica only knows about public key, and requester replica only knows about private key, and private key is generated using public key. So if any manipulation happens, then the private key will not maintain the pattern, and the requester replica will be able to detect that, okay, so something rules have been violated. So that's why the decryption becomes failed. So it ensures a secure communication between the requester and the requester replica. So that is why to ensure security, I have integrated asymmetric encryption in this project. Okay. So this is the overall system design and implementations. Before going to evaluation, I would like to explain my implementations codes and show a demo. Okay, give me the time. Okay. So make it a little bit bigger. Okay. So these are the codes. So here replica communication. So this is from SymPy. I have modified it. So in my project there is two mode. If the mode value is 0, so it determines without trust, I mean the existing CRDT. And if the mode value is set on, then it shows the output of after integrating the trust. So from here there is a broadcast pipe and message generator. So message generator is replica here generates the message synchronization request, and you see put the put message actually after generating a message, the requester replica puts the message in broadcast pipe, and so actually for PN counter value I have used some random methods. If and based on the random value I have done whether it is incremented or decremented, and message consumer where the request replica receive the message. So if you see here I have used decrypt, that portion I'll go later. So if the decision is accepted, then something happened, then the value of the requester replica is updated. But if it is ignored, then you see only the requester replica trace metric is changed, but the value of the requester replica is not updated, because in that case the requester replica is considered not trustworthy. So that's why the synchronization request from the requester replica didn't accepted by the requester replica. So this is on, and actually here I have used four replica A, B, C, and D. And after generating the message, replica A push the message in broadcast pipe. And simulations time, I have run these simulations for 30 seconds, I mean 5 minutes. Okay. So this is the SLE script. So this is yeah, here. So these are the rules I have explained in my presentation. So these are the value of these are the range of the trace matrix, and this is the uh, accepted range of the delta value. And here actions. Okay, so let me explain something else here. Like if the okay, if the decision is accepted, then the trust value of the requested replica is upgraded so that for future requests it can be considered most trustworthy. But you see, if the decision is ignored in that case, if the decision is ignored in that case, the trust value of the requested replica is downgraded. That is normal, and the threshold value of trust is from 0 to 100. Okay, but you may ask the questions here. The decision is ignored, but why? Why based on the value checked true, the trust matrix is updated. Okay. So if you see the rules, so for example, there it depends on two things. One is what is the value of delta and what is the current trust value of the requested replica. So it sometimes may happen that, for example, replica A for sometimes making non-trustworthy replica. So that's why the others replica downgraded its trust value. But I mean that happened. For example, somebody hacked replica A, but or maybe sensor malfunction happened to replica A. That's why replica A started making non-trustworthy request, and so the others replica detected that and downgraded its value. But after some times, replica A recovered, and now it has started making legitimate request. But now the request is legitimate, but the trust value of replica is still so down. So that's why the others replica will not accept the request, but if what they will do, they will upgrade the trust value of replica A so that at certain point replica A can be again considered trustworthy and it can continue operating in the distributed system. So that's why if the check value become true, then if still the decision is ignored, then the trust value will be upgraded so that eventually that particular replica become trustworthy again. Here are some helper methods. So these helper methods for I have used to parse the information. I have used SQLite DB file, and this helper method for generate the table for the DB file. And here goes the I have used Python provided PyCryptodon to do the encryption and decryption things. Okay, now let me simulate my project. So first I will show you without the trust. Okay, so that's why I have set the mode 0. Now I will run it without trust. Now I will simulate my project without the integration of trust management, like the existing CRDT, like the traditional CRDT. So now the simulations will be based on existing CRDT. Okay, so simulation times is 30 seconds, so it will take some time. You see, the DB file for every replica is generated, and now these are generated because in the helper method also I have said if mode equal 1, then the DB file will be generated inside the with trust directory, but otherwise the DB file will be generated inside the without trust directory. So now I set the mode 0, like without trust. So that's why the DB file have generated in without trust directory. You see, there are four replicas and they are communicating among themselves. It shows the things. And initially, every replica's values are 0. So when it started operating, every replica has the value 0. And every replica has trust metric 50%. Like that, the initialized thing. almost there. Okay, so without trust, the simulation is complicated, and the final Mars value 401. Okay, so these are the DB file. Let me open the DB file. Okay, okay, so without trust. So here I am just opening the replica SDB file and browse data. So you see the columns here. So here request as updated as those two columns are empty because for existing CRDT there is no concept of trust, and it shows what is the operations time, what is the request value. So you see whatever the request value is. So for example here, uh, so these are the requester replica. So the requester replica was D, and the current value of replica A was 6, request value was 4, and it was the type increment. Then the final value became 6 plus 4 as increment become 10, and whatever the request is, it is accepted. So sometimes you see it requested with some large value like 13, 14, 13, 15. So whatever happens, the requester replica accepted the request, and within a short simulation time, like 300 seconds, so this value becomes goes from 0 to 401, which maybe we can consider a large jump. So that is the simulation result from the existing CRDT pattern without any integration of trust. Now I will simulate the same simulations but with trust. So that's why I will set the mode on. Okay, okay, okay. Now I have, so you see something. So it here I just printed while debugging. I just printed the encrypted value here. So now you see the DB file has been generated in with trust directory. Okay. So meanwhile, while the simulation is running, I can go through the rest of the presentations. Okay. Okay, so this is the evaluation result. I evaluated for 4 replica ABCD, and this is the screenshot of the final portions that I showed here. You see the simulation ended with the value 4 on. So within a short period of time, the replica's value went from 0 to 401. Okay, and this is the final result of evaluations with trust. So here you see some there are value in the request trust and updated trust, and if you see if the accepted, then that time the requester replica value was 7.75, but if that request was accepted, its value was upgraded by 5, it became 80. But when it ignored, for example here it ignored, okay, this is the last portion, so that's why this replica became 0, but I will explain it from the db generated db file. Because the simulation, no, not this one, the simulation is still ongoing. Okay, okay, so I mean, you may ask what are the meaning of these values. Actually, these are the value I have specified for this project. But the rules, I mean, here the rules, the range of trust and the accepted range of delta can be different based on the data structure or based on the application's domain. For example, if the replicas are deployed to uh, keep track of the product counts in a retail store, in that case, I mean, based on the demand or based on the situations, based on the application's domain, this value will be different. But if these replicas are for collaborative text editor, in that case, so the rules will be different also. So actually here I have done some abstractions. It doesn't contain any real-time value because the real-time value will be based on the application's domain, based on the users, based on the developers, what they want to do. But here it shows that, okay, previously every request accepted whatever the requester value is, and the value ended 401, which is very large. But here they ended for same simulation, the replicas ended at value 35, which we can be considered reasonable for a short period of time, like 30 seconds, sorry, 300 seconds, I mean 5 minutes, we can consider. So here, if there are request which is not legitimate, that request was ignored. So after integrating this autonomous trust, it prevents error data to propagate across the system. So that's the motto of the project. I mean, otherwise, ill data can propagate across the system, and eventually the whole system will be polluted with wrong data. But after integrating the autonomous trust management, it can prevent so that wrong data cannot be propagated across the system, to make sure that the system still have right data and the system is still performing well. Okay, so that's was the motto of this project, goal of this project. So now here is the conclusion. Okay, let me check if the okay, so the simulation is completed, final value 35. Okay, so now let me open a database, but here it's I'll go with trust. Okay, okay, so here you see the final value is 35, and you see here the requester replica stress value is 50, but as the request ignored, its stress value downgraded to 45, and the current value 7 as request value 11, so it was rejected. So that's why the current value of the replica is still remained as 7. It didn't become otherwise different value. So that's why it prevented for wrong data to propagate across the system. Okay. So to conclude the project, I will say that after integrating the autonomous task management, a replicated data system, I tried to solve ill data to be propagated across the system. And you may ask why it is called autonomous task management, not only task management, because you see the trust value of requester replica is also updated based on the synchronization request a replica is making. So the trust value of requester replica is not static, it's dynamic and it is changing. So that's why I'm calling it autonomous. And the replica itself is changing it based on the interactions with other replica. Okay, another thing, I have leveraged service level agreement to define the rules, how the trust management scheme develop under different kind of synchronization request, and to ensure a secure communication between the replica, I applied asymmetric cryptography. So actually in distributed computing, trust management service level agreement are used, but they have been used in different domain. But in this project, I have tried to integrate task management and service level agreement, this technology, in the same domain. So that's, I think, that's on nobility of this project. So I mean, SLA and task management are used, but in differently. But here I have tried to integrate this technology in the domain of distributed replicated data systems. Okay, so in future plan, so here I have used 4 replica. In future plan, I would like to deploy this autonomous task management framework with many replicas in a different operating environment and platform. Like here, I have used my Ubuntu desktop computer. Maybe in future, I would like to deploy different replica in different devices, like some Raspberry Pi, some Windows computer, something like that. And at this moment, actually, in my project, it can detect suspicious requests, but it cannot specify what is the reason. I mean, if it is manipulated by any external attack, or if the reason of not legitimate request is sensor malfunction. So at this moment, my project cannot detect it. In future, I will try so that the requester replica can determine what is the reason of not legitimate request. And another future plan is to use different kind of data structure like graph, set, map. So in this project, I use counter, and also if I get very good results, then I plan to integrate this idea without I plan to integrate this idea to existing applications without changing the application's business logic. So that's all overall my project. Thank you very much. And if you have any questions or any improvement suggestions, feel free to email me. And if you feel that you want to explore the implementation code also, feel free to ask me. I'll share the code base with you. Thank you very much. Thank you. Thank you.